All right, hello everybody. This week we are gonna be doing Coriolis acceleration, so I'm just gonna write that down. Yeah, that's correct. Coriolis acceleration analysis. There we go. So, and we're gonna do 3 problems. And we're just gonna be talking about this new type of acceleration that we need to take into account for our kinematic problems. So, the first problem that we have, problem number 1, we have a block A which is attached to a cord, moves along the slot of an horizontal forked rod. At the instant shown, the cord is pulled down through the hole at O with an acceleration of 4 meters per second square, and its velocity is 2 meters per second. Determine the acceleration of the block at this instant. The rod rotates about O with a constant angular velocity of omega equal 4 radians per second. Alright, so we are giving here our system, our mechanism, and basically we're gonna have this forked rod that is gonna be rotating about point O, and at the same time inside that rod we're gonna have a block A that is gonna be moving with the entire system, but also moving towards point O independently, right? So we need to calculate the acceleration of point A. So basically the acceleration of the rod. All right. So we need to find the acceleration A, and to do that I'm just gonna go ahead and I'm gonna write the equation, the kinematic equation to calculate that acceleration. So the acceleration of A is gonna be equal to the acceleration of point O using the relative motion equation, right? Plus the acceleration of A respect O. And that acceleration is gonna be decomposed. I'm actually gonna write omega right here. So it's gonna be decomposed into components. The tangential acceleration, which is this first component, and the normal acceleration, which is the second component. And as you can see here, we're gonna have double cross product. So let's write that down. There we go. All of these guys are vectors, so we need to indicate that. But however, for this specific problem and for this mechanism, we are also gonna have another term, which is the Coriolis acceleration term, which is basically twice or 2 times the angular acceleration, no, the angular velocity, cross product the velocity of A respect O, and then finally we're gonna have the acceleration. Actually, let me rewrite this just like this is gonna be respect the coordinate system of x, y, and z, and also the acceleration of point A respect O of that reference coordinate system x, y, and z. All right, also a vector right there. Okay, so this is our equation now. Let's see what is every single term of this equation and analyze that. So this acceleration right here, it's gonna be the acceleration of point O, but point O is not translating at all, it's just rotating. So that acceleration right there is gonna be equal to 0. Right, the second term right here, like I said, this is gonna be the tangential acceleration of A respect point O. The second term right here is gonna be the acceleration of A respect point O, but now it's gonna be the normal acceleration. Then we're gonna have the Coriollis acceleration, and this last term, which is the acceleration of point A respect O from moving reference system. Alright, so let's go ahead and try to solve for this. So let's see. This first problem is going to be pretty straightforward. So we know that the acceleration of point O is 0 plus, here we're going to have omega dot, which is alpha, which is the angular acceleration, and that's given in the problem. Well, it's not actually given in the problem. Okay, so what is given in the problem is omega, which is the angular velocity, but that's gonna be constant for radians per second. So if it's constant, when we go ahead and we do the omega dt, which is equal to alpha or equal to omega dot, it's just gonna be equal to 0. So that tangential acceleration is also equal to 0. Then we're gonna have our normal acceleration, and that's gonna be 4k. Actually, I'm gonna go ahead and write my units here. It's gonna be okay, so it's gonna be 4 radians per second in the k direction, cross product again, and then cross product the distance from point A to O. Not quite the distance, it's gonna be the position, so it's gonna be a vector, and that's gonna be 0.1 meter in the I. We're gonna put our parentheses right here, which means we first need to solve for this term, and then we multiplied it by 4 radians per second. Alright, then we're gonna have the Coriolis acceleration, which is twice the angular velocity, and that's gonna be 4 radians per second k cross product, and that's gonna be the velocity of A respect point O, and that's given in the problem. It's gonna be 2 meters per second, but it's gonna be negative because it's going against it's gonna go opposite to the given coordinate system. So that's gonna be -2 meters per second in the I. And finally, we're gonna have the acceleration of A respect O, but we know that the velocity of A respect point O is constant, which means that this acceleration is gonna be equal to 0. Alright, so we get our equation set up right here, and we're just gonna go ahead and solve. What I'm gonna do first, I'm just gonna solve for this term. I'm gonna call it term 1. Actually, I'm just gonna call it what it is. It's the acceleration of A respect O, the normal component. And this one right here is gonna be my Coriolis acceleration. Okay, so we're gonna start solving for the first term. And that's gonna be equal to 4. I'm gonna drop my units at this point, but they're just gonna be the same. It's gonna be 4k cross product. Now I do my cross product right here, and that's gonna be 0, 0, 4 in the k, and then we're gonna have 0.1 in the I and 0 and 0, right? This cross product right there. So we go ahead, we solve for this. Basically, we can have a second cross product, which is 0, 0, 4 k from here, from this 4, and then we're gonna have from this cross product, we're gonna have 0.4 in the j, so that's gonna be 4.4 in the j. Okay, good, and that's gonna be equal to minus 1.6 I. Okay, good. Now we're gonna go ahead and we're gonna solve for the Coriolis acceleration, and same, but now this 2 is just gonna be a scalar. I'm just gonna multiply here our cross product. Let me see if I'm doing that right. 4 in the k and minus 2 in the I. Okay, that's right. And if we go ahead and solve for the entire thing, we're gonna have minus 16 in the j. Okay, good. And think, all right, I think something that wasn't quite right. This term right here, the acceleration of A respect to O, it's actually given in the problem, so it's not equal to 0. It's equal to 4 meters per second square in the I, but also pointing towards 0.0, so it's gonna be opposite. It's gonna be negative. If I can, it's gonna be negative. Okay. All right. So that's important because that's gonna sum to this acceleration, and we are gonna have that the acceleration at A is equal to minus 5.6 I minus 16j meters per second square, and that's our acceleration of block A inside the forked rod. Alright, so we're gonna proceed and we're gonna do another problem that is gonna be similar to this one, but that's how we're gonna give some practice to this type of problems. Okay, so for this problem, color C moves along rod BA with a velocity of 3 meters per second and an acceleration of 0.5 meters per second square, both directed from B towards A and measured relative to the rod. at the same instant, rod AB rotates with the angular velocity and angular acceleration shown. So this data right there. Determine the color's velocity and the acceleration at this instant. Okay. Okay. So let's see what we have here. Again, so what we need to find is gonna be the velocity of C, right? The velocity of the color and the acceleration of the color. Both of them are gonna be vectors. I don't know if we need to calculate the magnitude. That's not a problem. As soon as we get the vector, but let's go ahead. So we're gonna start with velocity at point C because that's just gonna be easier using this reference frame. We're gonna have VB plus omega AB cross product the distance from C to B, right? RCB plus the velocity of the color C, so the relative velocity. So this velocity is basically this 3 meters per second. It's the velocity of this color without any motion consideration of the rest of the system. Okay. Alright, so we go ahead and let's see. So the velocity of C is equal to velocity of point B. The velocity of this point is going to be equal to 0 because this point B is not translating at all. It is rotating but not translating. So that's going to be 0 right there, and then we're going to have the cross product of omega AB, which is given, and it's going to be positive in the K. And we're going to have the cross product of the distance CB, and that's going to be 0.5 in the J, in the Y, right? Meters in the J. Okay. And finally, we're going to have those three. So plus 3 meters per second in the J. So now we know how to do our cross product, and if we go ahead, we solve for that, we're going to have that the velocity at that of that color B is going to be minus 3I plus 3J meters per second. Alright, so actually let's go ahead do a quick drawing here. If we see the side of this system, we're gonna see something like this. Actually that's not gonna be the best way to draw this. Okay, I'm gonna take that back. What we are gonna see, this sketch is gonna be drawn from the top. Okay, so basically we're just gonna see something like this. Here we're gonna have like this base with the bolts attached to the ground, and here we're gonna have this collar. Okay, the collar by itself is moving with a velocity of 3 meters per second. Okay, and that's given by the problem. At the same time, this is rotating with this omega velocity, right? Angular velocity, and that's gonna produce a velocity tangential to the circular path, and it's gonna be something like that. And if we look at the result right here, we can tell that it's gonna be minus 3 meters per second in the I direction. So basically, this is gonna be omega AB cross product RCB. Okay, so the velocity of that color is the one that I'm gonna draw here. This velocity, that's the real velocity of the color. Okay, that's just like a graphical analysis of the problem. That's gonna be the actual velocity. So now we're gonna do a similar thing, but we're gonna solve for the acceleration. Okay, acceleration in the at point C, so vector is gonna be equal to this very long equation that we already drew before. So I don't know if I can. Okay, there we go. So we're gonna go ahead, we're gonna write that down. So it's gonna be AB plus omega dot AB cross product RCB plus the normal component, which is omega AB cross product omega AB cross product RCB. And all of these guys are vectors plus 2 omega AB cross product the velocity relative in the x, y, and z, and that's gonna be the Coriolis acceleration times the relative acceleration in the x, y, and z coordinates. All right, so let's see. This term right here is equal to 0, but that's gonna be the only one. So we have that AC is equal to 0 plus, here we're gonna have 1.5 k radians per second cross product 0.5 j plus the angular velocity, and that's gonna be 6k cross product 6k again and cross product 0.5 j. Okay, now the Coriolis acceleration is gonna be 2 times 6k, which is the angular velocity cross product the relative velocity, and that's given in the problem 3 meters per second in the j, and finally 0.5 meters per second square in the j. So solving here this vectorial equation, we're gonna end up having that the acceleration of point C, there we go. So the acceleration of the color is equal to minus 36.75 I minus 17.5 J meters per second square. All right, so the problem number 2 is done. Pretty similar to problem and number 1, but now probably we're having a better understanding of this type of problems and how they need to be analyzed. Okay, so now we're gonna proceed to do the last problem. So for this problem, the crane's telescopic boom rotates with the angular velocity and angular acceleration shown. So right here, this piece of data. At the same instant, the boom is extending with a constant speed of 0.5 feet per second. So let's see, we're gonna have that the velocity of B respect A, the reference frames X, Y, Z is equal to 0.5 feet per second, which means that AB on A, I'm sorry, A acceleration of B respect A, the X, Y, Z is gonna be equal to 0 because the velocity is constant. Determine the magnitudes of the velocity and acceleration of point B at this instant. Alright, so now we need to determine the magnitudes. So we're gonna proceed in a similar way that we did before. So what we're gonna do, we are going to go ahead and write down the velocity equation. P is equal to VA plus omega AP cross product REA plus this given velocity. Okay, so VA for this, so this point right here, it's not gonna be translating. It could be, but it's not. You know, like if this entire crane is moving with a velocity, I don't know, whatever. So it's moving a given velocity, then that point A would be have a velocity, but that's not what's happening. That point is steady, and that velocity is equal to 0. Okay, we keep solving for this, same as we have done before. We're gonna have a negative angular velocity, which is 0.02, the K cross product 60 feet, the J. And now you might want to know where is the coordinate systems that I'm using. So the coordinate system that I'm using for this problem is gonna be X in this direction and Y in that direction. Okay, so now that makes sense, right? Like we have 60 and then yeah, K negative, okay, that's okay. And then we also need to add positive 0.5 J, which is the 0.5 meters per second, no, feet per second here given in the problem. So we go ahead, we solve for this, and we're gonna have 1.2 I plus 0.5 J. That's gonna be meters per second, but that's gonna be the vector. So we just need to do the square root of those two components to get the magnitude. And that's gonna be equal to 1.3 feet per second. And feet per second here as well. Okay, so that's the first part of the problem. And the second part of the problem is gonna be similar to the previous one, right? The two previous problems that we have done. And in fact, I'm just gonna try to Okay, I don't know if my computer is having a real hard time right here. Let me see. I'm just trying to, no, whatever. I'm just gonna rewrite the entire thing. I was trying to copy that big long equation, but that's not gonna happen. Okay, let's do that. It's very important for you to know what every single term in this equation is, because that's gonna allow you to solve any type of these problems. Okay, now we have our Coriolis acceleration term. Finally, the relative acceleration in x, y, z. Right, so if the velocity of point A is equal to 0, then the acceleration it's gonna be equal to 0 because point A is not moving at all. And the velocity of the boom, of the telescopic boom, is constant, so acceleration is equal to 0. So those two terms are gonna be equal to 0. Right, then you can go ahead, do all the math here. So we have 0 plus minus 0.01 k, that's the angular acceleration, cross product with that 60 feet, the j, first term, right there. Then we can have the omega AB minus 0.02 k cross product minus 0.02 k again, cross product 60j. That's the normal component. Finally, we're gonna add the Coriolis acceleration. All right. So we go ahead, we solve for this, and acceleration at point B is equal to 0.62 I minus 0.024 J feet per second square. And again, we need to calculate the magnitude. So we just need to do the square root of the two components. And that's gonna be equal to 0.6204 feet per second square. So yeah, we can see that the most part of the acceleration is going in the I direction, since the J right here is very, very small. Alright, I think this is gonna be all for this week. As we have done in the previous weeks, I'm gonna post on BBLearn worksheet, and you will need to do it and submit it. And let me know if you have any question. Email me. I'll be happy to help you out with that. Have a good week.